A cosmic mystery. The search for a theory of everything. The universe is a place of awe and wonder. From the smallest particles to the largest galaxies, it operates according to a set of fundamental laws. Physicists have long sought to uncover these laws, driven by a quest for a single, elegant theory that can explain everything. This elusive goal is known as a theory of everything. Imagine a theory that could explain the behavior of all matter and energy in the universe. A theory that could account for the force of gravity, the interactions of subatomic particles, and the evolution of the cosmos from the Big Bang to the present day. This is the ultimate goal of a theory of everything. The search for such a theory is one of the most ambitious scientific endeavors of all time. It requires a deep understanding of both the vastness of the universe and the intricacies of the quantum world. While a complete theory of everything remains elusive, scientists have made significant progress in their quest to unify the laws of physics. This essay will explore the history of this quest, the current state of research, and the potential implications of finding a theory of everything. It will delve into the mind-boggling concepts of string theory, extra dimensions, and the unification of general relativity and quantum mechanics. The journey will take us to the very edge of human understanding, where the known meets the unknown.
Einstein's dream unifying the forces of nature. Albert Einstein, one of the most brilliant minds in human history, spent much of his later years pursuing a unified theory of physics. He was driven by the belief that the universe's apparent complexity must stem from a simple and elegant set of underlying principles. Einstein's work on general relativity, which describes the force of gravity as a curvature in space-time, revolutionized our understanding of the universe. However, he recognized that his theory was incomplete. It could not explain the other fundamental forces of nature, electromagnetism, the weak nuclear force, and the strong nuclear force. Einstein's dream was to find a single framework that could encompass all four forces. He believed that a unified theory would reveal deep connections between seemingly disparate phenomena, offering a more complete and profound understanding of the universe. While Einstein's quest for a unified theory ultimately proved unsuccessful, his vision continues to inspire physicists today. His insights paved the way for subsequent generations of scientists to develop new theories and explore uncharted territories in their search for a theory of everything.
The Kaluza-Klein theory, an early attempt at unification. One of the first attempts to unify gravity with another fundamental force came in the early 20th century with the Kaluza-Klein theory. Theodor Kaluza and Oscar Klein, inspired by Einstein's work, proposed a radical idea that the universe might have more than the three spatial dimensions we experience. Their theory suggested that electromagnetism, the force responsible for light and electricity, could be explained as a manifestation of gravity in a hidden, curled-up fifth dimension. Imagine a garden hose. From a distance, it appears as a one-dimensional line, but up close we see that it has a second curled-up dimension. While the Kaluza-Klein theory was ultimately unsuccessful in its original form, it introduced the groundbreaking concept of extra dimensions. This idea would later resurface in more sophisticated theories, such as string theory, which also proposed the existence of hidden dimensions to unify the forces of nature. The Kaluza-Klein theory, though flawed, served as a stepping stone in the quest for a theory of everything. It demonstrated the potential power of unification, suggesting that seemingly distinct phenomena might be different facets of a single underlying reality.
The quantum revolution, a new perspective on the universe. In the first half of the 20th century, physics underwent a revolution with the development of quantum mechanics. This new theory, which describes the behavior of matter and energy at the atomic and subatomic levels, revealed a universe far stranger than anyone had imagined. Quantum mechanics introduced the concepts of wave-particle duality, uncertainty, and quantization, challenging the deterministic worldview of classical physics. It showed that particles can behave like waves, that certain properties like position and momentum cannot be known simultaneously with perfect accuracy, and that energy exists in discrete packets called quanta. The quantum revolution had a profound impact on the search for a theory of everything. It became clear that any successful unified theory would need to reconcile the seemingly contradictory worlds of general relativity, which governs the universe on large scales, and quantum mechanics, which reigns supreme in the realm of the very small. While general relativity describes gravity as a smooth curvature of space-time, quantum mechanics portrays the other forces as arising from the exchange of discrete particles. Unifying these two fundamentally different frameworks has proven to be one of the greatest challenges in modern physics.
Imagine the universe as a grand symphony, every particle, every wave contributing to a cosmic melody. This is where theories like string theory come into play. They suggest that at the most fundamental level, everything is made of tiny vibrating strings. These vibrations create the different particles and forces we observe. It's like the strings of a musical instrument, each producing its own unique note. Fascinating, isn't it?
General relativity, formulated by Einstein, describes the gravitational force as a curvature of space-time caused by mass and energy. It's incredibly successful at explaining the behavior of large-scale structures like planets, stars, and galaxies.
Quantum mechanics, on the other hand, deals with the subatomic world. It explains the behavior of particles at the smallest scales, where the rules of classical physics no longer apply. It's a realm of probabilities and uncertainties, quite different from the deterministic nature of general relativity.
The challenge is that these two theories don't quite fit together. General relativity works exceptionally well on a large scale, while quantum mechanics is incredibly accurate at the microscopic level. But when we try to combine them, things get, well, complicated.
Yeah, and that's where a lot of modern theoretical physics is focused. Finding a way to reconcile these two pillars of science into a unified framework. It's like trying to piece together a puzzle where the pieces don't seem to match up perfectly. But that's what makes it so exciting.
A theory of everything, often abbreviated as TOE, represents the ultimate goal in physics. It aims to unify all fundamental interactions of nature into a single, all-encompassing framework. Such a theory would not only deepen our understanding of the universe, but also provide insights into the very fabric of reality. Imagine being able to describe every force, particle, and interaction with one elegant equation. This is the profound significance of a theory of everything.
So, where do we stand with experimental evidence? Well, it's a mixed bag. We've made incredible strides with the Large Hadron Collider and other particle accelerators, revealing particles and forces that were once purely theoretical. But there's still so much we don't know. Future directions might include more advanced accelerators, space-based observatories, and even new technologies we haven't yet imagined. The quest for experimental evidence is ongoing and ever-evolving.
The pursuit of a unified theory isn't just a scientific endeavor. It has deep philosophical implications. Throughout history, humanity has sought to understand its place in the cosmos. A theory of everything could potentially answer age-old questions about the nature of existence, the origin of the universe, and the fundamental principles that govern reality. It challenges our perceptions and invites us to rethink our understanding of life and the universe.
The journey towards a theory of everything is far from over. Scientists around the world continue to push the boundaries of knowledge, driven by curiosity and a desire to unlock the mysteries of the universe. This ongoing quest for cosmic understanding is a testament to the human spirit, showcasing our relentless pursuit of truth and our unending fascination with the cosmos. Each discovery brings us one step closer to comprehending the universe in its entirety.